Christmas 2004. Amazon's website is melting. Every web server is waiting on one Oracle database. Engineers are manually tuning queries at 2 a.m. Werner Vogels, Amazon CTO, calls it the database problem. Adding more web servers did nothing. They all queued at the same bottleneck. Fast forward to Prime Day 2021, DynamoDB serves 89.2 million requests per second. Single-digit millisecond latency. 0 planned downtime. That number is the highest throughput ever publicly recorded for a managed database. Here's exactly how it works. These aren't marketing numbers. These are production measurements. DynamoDB stores hundreds of petabytes across thousands of storage nodes globally. It powers Amazon's shopping cart, Alexa, Netflix's session store, Lyft's ride matching, and Samsung's SmartThings simultaneously. Every get-item call returns in under 10 milliseconds, regardless of table size. A table with one item and a table with 10 billion items get the same latency. That's not luck. That's architecture. Let's peel back every layer, starting with how Amazon reached these numbers from zero. Amazon's original Oracle database had 4 fatal failure modes at scale. First, cross-shard joins. A single product page needed data from 4 different shards: inventory, pricing, reviews, descriptions. Each cross-shard join added 10 to 100 milliseconds. 4 joins meant 500 milliseconds page loads. Amazon's SLA demanded under 50 milliseconds. Second, schema migrations took 7 to 14 days on a 500 million row Oracle table. During peak season, that's impossible. Third, distributed two-phase commit creates a coordinator single point of failure. One coordinator crash leaves locks held indefinitely across all shards. But here's the catch. The real problem was operational complexity, not just latency. Think of consistent hashing like a circular clock face. Every storage node gets a position on that clock. Every data key gets hashed to a position on the same clock. The key goes to the nearest node clockwise. DynamoDB uses a 128-bit hash ring. Positions range from 0 to 2 to the power of 128. When you add a new node, only the keys between the new node and its predecessor need to move. That's roughly 1 divided by n of total data. With simple hashmod sharding, adding one node reshuffles nearly all keys. At thousands of nodes, consistent hashing makes node changes safe online operations. Now here's where it gets interesting. Virtual nodes. Every write in DynamoDB follows a strict path. The client sends a PutItem request. It hits the request router, a stateless fleet handling AWS SIG-v4 authentication and IAM authorization. The router hashes the partition key to find the correct storage node. That node's leader replica receives the write. The leader appends it to the write-ahead log first, a sequential disk write. Then it replicates synchronously to 2 secondary replicas across different availability zones. Once 2 of 3 replicas acknowledge, the write is confirmed to the client. The B-tree update happens asynchronously afterward. This is why DynamoDB writes are fast and durable at the same time. DynamoDB's storage engine uses 2 data structures working together. The B-tree lives on SSD and handles all reads. A B-tree lookup on 1 million items requires only 3 to 5 disk seeks. That's predictable, bounded latency, critical for a single-digit millisecond SLA. Cassandra uses LSM trees instead. LSM trees write faster but compact in the background, causing unpredictable read latency spikes. DynamoDB rejected that trade-off. For writes, DynamoDB uses a write-ahead log. Every write is a sequential append, O of one-time complexity. Wall entries sync to disk before the client gets a response. Crash recovery replays the wall to rebuild the B-tree. This is why engineers lose sleep designing storage engines. One wrong choice destroys your latency guarantees. Every DynamoDB partition has exactly 1 leader replica. All writes go through that leader. But what happens when the leader crashes? If 2 replicas simultaneously believe they're the new leader, both accept writes. That's split brain. In a payment or inventory system, split brain means 2 replicas disagree on your account balance. DynamoDB uses Multi-Paxos to make this mathematically impossible. A candidate sends prepare with epoch n to all 3 replicas. It needs 2 of 3 promises, a quorum. 2 candidates cannot both hold 2 of 3 votes simultaneously. They share at most 1 vote. The quorum intersection property means only 1 leader can ever hold quorum. The math doesn't negotiate. Lyft uses DynamoDB for ride state management. 2 drivers cannot accept the same ride simultaneously. This is a classic race condition. DynamoDB solves it with conditional writes, a condition expression that only succeeds if the item's current state matches your expectation. If driver A and driver B both try to accept ride 42, only one succeeds. The other gets a conditional check failed exception. No locks held, no deadlocks possible. This is optimistic concurrency control. Assume no conflict, verify at write time. At Lyft's scale, this pattern handles millions of concurrent ride state transitions without a single distributed lock. Here's a problem that destroys production systems. You provision a DynamoDB table with 1,000 write capacity units. That capacity spreads evenly across 10 partitions, 100 WCU each. Now a viral product gets featured on Amazon's homepage. Suddenly 90% of writes hit one partition. That partition hits its 100 WCU ceiling. Writes start throttling, even though 900 WCU sit idle across other partitions. Before adaptive capacity, engineers manually restructured partition keys. DynamoDB's adaptive capacity detects hot partitions within minutes and automatically redistributes capacity toward the hot partition. It also uses partition splitting. A partition over 10 GB or over 3000 RCU automatically splits into two. Transparent to your application. Zero downtime. Netflix stores over 600 billion items in DynamoDB. Their session store tracks every active stream. PutItem fires when playback starts. Update item fires every 30 seconds with your playhead position. Get item fires when you resume. With 260 million subscribers potentially streaming simultaneously, that's hundreds of millions of concurrent active sessions. Netflix also uses DynamoDB's global tables for their viewing history. Writes in US East 1 replicate to EU West 1 within seconds. Both regions accept writes simultaneously. If AWS US East 1 has an incident, EU West 1 serves all European traffic without failover configuration. This is active-active, not active-passive. Netflix's architecture requirement was exactly 0 RPO, near 0 RTO. DAX, DynamoDB Accelerator, sits in front of DynamoDB as an in-memory cache. It reduces read latency from single-digit milliseconds to microseconds. DAX uses an item cache for get item and a query cache for query and scan operations. Cache invalidation is automatic. A write through DynamoDB also invalidates the DAX cache. Gaming leaderboards, real-time bidding systems, and session stores use DAX to absorb read spikes without hitting DynamoDB storage nodes at all. Airbnb uses this pattern for availability calendars, high read-to-write ratios where DAX absorbs 95% of reads. Combined with global tables, your application writes to the nearest region and reads from microsecond cache locally. Most engineers use DynamoDB wrong at scale. First, never use a low cardinality partition key. Using country as a partition key with 10 countries means 10 partitions maximum. You'll never distribute load effectively across thousands of nodes. Add a random suffix or composite key. Second, DynamoDB charges per WCU based on item size, 1 WCU per 1 KB. A 10 KB item costs 10 WCU per write. Keep items lean, store large blobs in S3. Third, use sparse indexes. A global secondary index only includes items where the indexed attribute exists, dramatically reducing index size and cost. Fourth, DynamoDB Streams plus Lambda gives you zero polling event-driven pipelines.